All right, so we're dealing with capacitance. Capacitance is going to involve capacitors. And we will just charge it up. Charging up a capacitor is going to involve a battery. That's where you get your voltage from. This one represents a positive charge plate. This is going to represent a negative charge plate. So you got your positive terminal here, you got your negative terminal here. Positive terminal is going to charge up one plate positively, negative terminal is going to charge up the other plate negatively. So this one is going to be positively charged. This one is going to be negatively charged. So how much charge you can place on a capacitor is going to depend on the voltage supplied by the battery. All right, so the larger the amount of voltage supplied, the larger the amount of charge is going to be. Okay, so I'm going to do something stupid. The stuff that I'm going to do, I consider somewhat stupid, is how do you get rid of a proportionality constant? All right, so this thing that looks like Jesus fish, those of you guys are Republicans, is a proportionality sign. All right, don't let that shock you. Okay, so how do you get rid of that proportionality sign? What do? Those of you guys who've been taking calculus, and some of you guys are taking differential equations, and this is the approach I absolutely passionately hate that physicists use. They go, oh, there's a proportionality sign, man, like the Jesus fish. So how do you get rid of it? So how do you get rid of it? Yeah, you get rid of it by putting a proportionality constant, right? Oh my God, look, I got rid of it. That was cute. This is a textbook dumbass explanation regarding how we arrive at capacitance. All of a sudden it becomes a proportionality constant, despite the fact that it is nothing like it. Most textbooks will describe it as such. Hey, I got rid of the proportionality. Now we got a proportionality constant. So this proportionality constant that you guys are looking at, it's got a name. It's called capacitance. What does that represent? It represents the ability to hold charge. All right, so this is going to represent the ability to store charge. Let's put store charge. All right, so capacitance is the ability to store charge. Capacitance is the capacity to store charge. Wow, that's major bullshit. Anyway, I don't like the book definitions. Textbook definitions is, textbooks are reference books. They're not that interesting. If you want to kill a subject, if you want to make it really boring, write a textbook about it. Okay, so I'm going to make room, and I'm just going to say the amount of charge that you can put on a capacitor is going to depend on not only the voltage that you get from a battery, also it's going to depend on the capacitance of it. I don't like to use it as a proportionality constant. I like to use it as is, which is kind of cute. So the question is, what is the capacitance depends on? All right, so capacitance is the amount of charge that you can place in the storage device, amount of charge that he can hold. So ability to hold a charge, I don't like that definition either. All right, so I'm just going to cross that over. It is the amount of charge that this storage device can hold. All right, so I'm going to make room. Keep changing my own definitions. I kind of like it. So it's the amount of charge that it can hold. That the device is going to be able to store. All right, so amount of charge that a storage device can store, charge storage device. It's not ability to hold a charge, it's got ability. It's the amount of charge that you can store on it. It's known as capacitance. All right, so larger the capacitance is, the more charge you can put on it. That's what it means. Larger this is, the more charge it's going to be able to store. All right, larger the voltage difference is, the more charge is going to be able to store. Larger the amount of energy supplied by the battery, the more charge it's going to be able to hold. Larger the capacitance is, more charge it's going to be able to hold. All right, so this ability to hold a charge, or the amount of charge that it can actually store, is going to be the capacitance. So what do you suppose the capacitance is going to depend on, if that's the case? All right, so it's very commonsensical until it stops being commonsensical. This is one of those things. Oh my God. So you got two parallel plate capacitors. I'm going to just charge it up by using a battery. All right, so let's just connect these. This one is going to be positive charge. This is going to be negative charge. Number one, the amount of charge that it's going to be amount of charge that it's going to be able to hold on is going to depend on the size of the area. All right, so It depends on the amount of room that you're going to be able to provide it with. So, which means that capacitance is definitely going to depend on the surface area onto which you can distribute the charge. So the first contributing factor, as far as I'm concerned, is the capacitance is going to be directly proportional to the area, the size of the area that's going to store the charge. More area you have, more charge you're going to be able to store. More area you have, larger the capacitance is. Smaller the surface area is, the less charge you're going to be able to store. All right, that kind of makes sense. The second one is, the second one is almost intuitive, just as intuitive as the first one is depends on the separation distance. All right, closer these opposite charge regions are to each other, the larger the capacitance is going to be. So the capacitance is going to be inversely proportional to the separation distance. All right, so smaller the distance is, the larger the capacitance is. And then we will do what the mathematicians do usually, get rid of the proportionality constant, which means that we have to turn this into some kind of an equation. And then we turn this into some kind of an equation and then in order to turn it into an equation, we will come up with some kind of a proportionality constant. All right, so that's what we will do. And that's where the common sense is gonna kind of take a backseat. So capacitance is gonna be directly proportional to the area. It's gonna be inversely proportional to the separation distance. Now that we're turning this into an equation, we have to put a proportionality constant here. All right, so the question is, yeah, we kind of get the proportionality constant, but why are we using epsilon naught? Why is this being used? Okay, so we'll ignore that question. All right, so this is the equation that we get to. Yeah, go ahead.
Garlic powder, onion powder, chili powder. Although you don't need onion powder because you're putting onions in it.
Okay, so that's good to know. So moving forward. All right, guys, meet yourselves. If you're going to have conversations about onion powder. Okay, so onion powder aside, what do we know? Capacitance depends on the area. Larger the surface area is, larger the capacitance is, so more charge is going to be able to hold. And it's going to be inversely proportional to the separation distance, which means that closer these two surfaces are, the more charge is going to be able to hold. Okay, so D represents the separation distance between the plates. Okay, so A is the surface area. D is the separation distance. Separation distance between two oppositely charged regions. Okay, so that's good. C is our capacitance. Say it's the ability to hold a charge. Or what did I say? Amount of charge that the capacitor can hold. Amount of charge that you can store in a capacitor is the capacitance. Okay, it's kind of like that. All right, so this is the formula. Main formula. Okay, so what do we have? Q is the net charge. This is the amount of charge that you can store. It's going to be in terms of Coulomb. All right, so V is the voltage supplied by the battery. It's going to be in terms of volts. And C, okay, guys, notice that's what C is. The C is going to be Q over V, right? Q is going to be in terms of coulombs, and V is going to be in terms of voltage. All right, so this is going to be coulombs per volts that you're looking at. So the capacitance can be expressed in terms of, it's going to be coulomb per volt. All right, it can be expressed like that, but that's not the way we will express it because it's just too much. So how do we express it? Isabel, you're okay. That was funny. I thought you were trying to answer a question. Anyway, okay, let's get back to the lecture. Oh my God, what do you know? Same formula. All right, so the amount of charge that you can store depends on the capacitance. That's going to tell you the amount of charge that you can store, the ability to store a charge, and it also depends on the voltage supplied by the battery, the energy supply. All right, so this is the symbol. Take a look at the units. Notice that the capacitance, instead of using Coulomb per volts, we end up using a symbol F. What does F stand for? We'll find out. Okay. So ability to hold a charge for a charge storage device depends on the surface area, how big the areas are, or the size of the areas, or the magnitudes of the areas. Also, it's inversely related to the separation distance. It's called F. F stands for farads. In the farads, it's short for Faraday. Okay, so speaking of Faraday, so instead of using this, which you're entitled to, it's every country, all right? Instead of using coulombs per volts, what we will do, we will use F. F stands for farads. Okay, now let's have a meaningful discussion about the meaning of this. All right, so coulomb is a charge unit. Volt is an energy unit. That's the amount of voltage. That's the amount of energy stored within the strength of the electric field. And F, farad, is the capacitance unit for capacitance. All right. Faraday, what's his nationality? Does anybody know? All right, guys, you're from the United States, you don't care. And then you go to Europe and then you get killed and you kind of wonder why. Nationalities do matter.
Faraday was English, wasn't he?
He was 100% English, yes. Give yourself 5 points for knowing that. Okay, very good. He was British. Faraday is British. And in fact, the entire course that I'm teaching, made possible by Faraday, as you're about to find out. This guy is British. Coulomb, what's his nationality?
French, right?
This guy's French, right? Okay, how about Volta? What's his nationality?
French.
He's not French, no.
Really?
I'm not kidding. He's not French. Volta is the original name. What's his nationality?
Italian.
Okay, 100% Italian. This guy's the pizza man. All right, you give yourself 5 points for that one. All right, so Coulomb, whoever picked that one, give yourself 5 points. This one is Italian. So what's happening here is you take a French and divide it by Italian, you end up getting a British. All right, so everything is international. Wow, this is called crossbreeding, almost like royalty. All right, so French, this guy is French, divided by Italian, it's just too much divisions, and then you end up getting a guy who happens to be British. So either you can say Coulomb per volt for capacitance, that's fine. Instead, in honor of Faraday, we call it farad or F, so which stands for Faraday. All right, a lot more about Faraday eventually. All right, guys, if you missed this one, I'm gonna kill you because I wasted like 5 minutes talking about this freaking nonsense. All right, so what's the best answer?
D. Let's go with D.
Yeah, it's A. Moving forward. All right, give yourself 2 points for that one.
Say 2 points.
2 points. I mean, I've been talking about it for 5 minutes. I mean, come on.
When a battery is connected between two pieces of metal, it forces charge to flow from one to the other until the potential difference between them is equal to the voltage of the battery. That creates an electric field between them. If the voltage is doubled, so is the charge. So is the potential difference. And so is the electric field. In general, the charge transferred is proportional to the voltage applied, and the constant of proportionality, C, is called the capacitance.
It's review after review after review after review. Hopefully one time it catches, guys. All right.